Okay, so now that you know how to write skeletal equations and balance them, it's time to take a look at the types of chemical reactions that we will be working with this year, and then some specifics about a few of them. So in general, there are 5 types of chemical reaction, but we also add a 6th extra one, and it's not that it's its own type, but it's a different category of chemical reaction. So the 5 that we start with are synthesis, decomposition, single displacement, double displacement, and combustion. Now the 6th one is called redox, which stands for reduction oxidation. And we're going to talk more about that later. That encompasses, in some ways, some of the other types of reactions would fit under redox, but there's more to do with that one. So we'll come back to it. To start with, we want to understand why we categorize reactions into different types. Well, it turns out that the different types of reactions are based on the nature of the reactants. And they all have different characteristics. They have different reactant types, different product types. And if you know the rules, you can now predict the outcome of mixing 2 things or 3 things together. You'll be able to actually predict what will happen once you know the types of reactions and their rules. That's our goal. Our goal is to be able to give you some information so that you can take a look at a couple of substances and figure out what would happen, if anything, if you put them together. Okay? Our goal is going to be to write balanced chemical equations, and for now we're writing what are called full molecular equations, meaning all of the formulas are full neutral formulas. Okay? We're going to change that a little bit later on too. So to start with, let's take a look at synthesis reactions. Synthesis reaction is simply a combination. Okay? We have 2 reactants, A and B, and we combine them to form one product. The word synthesis means to make, so we're making stuff. We're going to make one single product. That's one of the ways that you can tell that a reaction is a synthesis reaction if on the right-hand side there is one substance formula only. Okay? Now there are 4 subtypes of synthesis reactions depending on the reactants. We can react a metal plus a nonmetal together. We can react 2 nonmetals together. Then we can react a metal oxide and water or a nonmetal oxide and water. These are the 4 subtypes of synthesis reactions, but they all produce a single product. And that's the earmark of synthesis reactions. So we'll take a look at the first one, metal and nonmetal. Okay? If you put a metal and nonmetal together, you get a binary ionic compound. Be very careful because some metals, we know, have multiple positive charges possible, like lead, tin, iron, copper, and others. If you have one of those metals as one of your reactants, then just pick one of the oxidation states and go with that. Generally, we try to go with the one that's in bold on the periodic table. That would be the most correct, but you can use really anyone and you're not going to be wrong. Okay? If you have a nonmetal and a nonmetal, the product will be a binary, 2 elements, molecular compound. Okay? Now there are a lot of molecular compounds. We've studied a good number of them. All you need to do is pick one that contains the 2 nonmetals that you started with. Pick one that you know and use that one. Okay? For a metal oxide and water, our product is going to be the hydroxide of the metal. So a metal oxide is an ionic compound where the anion in that ionic compound is oxygen and the cation is a metal. A hydroxide is polyatomic ion, so a metal hydroxide will be the metal that you started with in the oxide plus the OH minus, the hydroxide ion. Okay? And hydroxides, any compound that contains hydroxide is considered a base. That's the opposite of an acid. Okay? If you're using a nonmetal oxide and water, you're going to make a common acid. A nonmetal oxide is a molecular compound where you have oxygen in it. Carbon dioxide, sulfur trioxide. Those are examples of nonmetal oxides. Okay? Write your acid formulas the way you normally do and just be able to name them. So here are some examples. I want you to take a minute, write these down, the descriptions down, and leave a little space under each one so that we can take a look at how we write equations for these reactions. Okay? So we have lithium metal added to nitrogen gas. We have powdered iron reacting with powdered sulfur. We have solid sodium oxide dropped into water, and we have sulfur trioxide gas bubbled through water. Write them down, leave a little space, and we'll write some equations once you're done with that. We ready? All right, well, let's take a look at the first one. We have lithium metal reacting with nitrogen gas. So lithium metal is Li, and it's a metal, so it's going to be solid. There's only one metal that's not a solid, and that would be mercury. So lithium is a solid. And nitrogen gas, nitrogen is one of the 7 diatomic elements. So it has to be N2 and gas. All right, so we have a metal plus a nonmetal. Metal plus a nonmetal, the product will be an ionic compound. So the compound is going to be lithium and nitrogen together, lithium nitride. Li has a +1 charge, nitrogen has a -3 charge, so Li3N. Now, the state for Li3N, this is a very important thing that you need to start to learn, is how to predict what physical state that's going to be in. Here's rule number 1 for doing that. If you are forming an ionic compound and there's no water anywhere in your reaction, so there's no water listed as a reactant or a product, and there's no aqueous solutions here, if that's the case, then your ionic compound must be a solid. Ionic compounds are all solids at room temperature, okay? Unless they're dissolved in water, but there's no water for it to dissolve in here. Now, I need to balance this. I have 3 lithiums and 1 nitrogen, so that means I have to put a 2 here to get the nitrogens to balance, and that gives me now 6 lithium, so I'll put a 6 in front of the lithium. So 6 Li plus N2 goes to 2 Li3N. That's our synthesis reaction, 1 product over here. Yes, you can have a coefficient that's not 1, but they're 1 formula over here. Okay, let's do the next one. So the next one was iron, metal, solid iron, powder, right? And powdered sulfur, S. Now here, we have another ionic compound, metal plus a nonmetal. But the problem is that iron has 2 possible positive charges. Iron can be +2 or it can be +3. And depending on which charge it has, you'll get a different formula for iron sulfide. So if iron is +2, S is always -2, you'll get FeS. Ionic compound, it'll be a solid, no water present. And that happens to be balanced the way it is. That's iron 2 sulfide. But if you decide that you want to use iron 3 for this reaction, which, to be honest, we probably should, because iron 3 is the preferred oxidation state, the preferred charge of iron. Fe +3 and S -2 will give you Fe2S3, which is also an ionic compound, therefore solid. But this is not balanced, so I need to balance them. I need to put a 2 in front of the Fe and a 3 in front of the S, like that. Either of these technically are correct for that reaction. The bottom one is a little bit more correct because iron prefers to be +3. All right, let's look at the next one. We have sodium oxide reacting with water. Sodium oxide, sodium is +1, oxide is -2, so that's going to be Na2O. And it says it's solid, so I'll put my S in there. And we're dropping it into some water, H2O, which is a liquid. Okay? Now, I know I'm only going to get 1 product over here. Okay? And according to my rules, this is a metal oxide. Sodium is a metal. Metal oxide plus water. We get the hydroxide of the metal. Well, the metal is sodium, and hydroxide is OH-. So hydroxide of sodium, sodium hydroxide, is NaOH. Sodium hydroxide. I'll come to the state symbol in just a second, because we have water now involved. Okay? Sodium hydroxide, so now I have to balance this. I have 1 sodium here, I have 2 sodiums over here. So let's put a 2 in front of the NaOH. So that gives me 2 sodiums on both sides. That gives me 2 oxygens, which I have, 1 in water and 1 in sodium oxide, and 2 hydrogens, which I have both in water. So this must be the answer. Now, the physical state of NaOH is aqueous for this example. Why is it aqueous? Well, here's the deal. Any ionic compound that contains an alkali metal will dissolve in water, always. And since there's some water involved, this stuff is going to dissolve. It's that simple. And I'm not simplifying it, that's just the rule. Any ionic compound that contains an alkali metal will be very soluble, and it'll dissolve in water if there's water around. So we're going to make this an aqueous solution. Now, we'll deal with this later because there's more that we'd have to do with this, but this is good enough for now. Okay? And finally, the last one that we had was sulfur trioxide gas is bubbled through some water. Sulfur trioxide is not an ionic compound. There's no metal in there. So it's a molecular compound. Sulfur trioxide means O3, and that is a gas. We're going to bubble this through water, H2O, which is also a liquid, and we're going to produce one compound. Well, this is not a metal, this is a nonmetal oxide. Nonmetal oxides plus water give me a common acid. Common acids that we've heard of before. Now the neat thing is that most of the time, all you have to do is just take what you've got here and combine them all together and make an acid out of it. Acids always have hydrogen in the front. And I had 2 hydrogens here. What I'm left with then is an S and 4 O's. Well, I can write SO4. That's sulfuric acid right there. Water's involved. Acids, when water is involved, are always aqueous. Acids are aqueous. What makes them acids is the fact that they're dissolved in water, so that the H+ ion is free to do its work. Okay? That is a nonmetal oxide plus water.